Welcome, everybody. Thank you for choosing to be with me here in this talk. As we were made aware this morning in the race of AI, a lot of information is put out there. And it's actually a privilege to get some attention of the people that can pick and choose from so many interesting talks here or other activities that will help you grow your knowledge. So thank you for being here. We're going to focus on you for starters. The spotlight is on me, but through the hard light, I can see a little bit from you, and we're going to zoom in on you a little bit further because I'm a curious person. And I built this thermometer that will help me get to know you a little bit better. So in the next few slides, I want you to raise your hand, showing what's true for you in the thermometer I built. So let's see, the first question is, what's your urge when someone says AI? Do you want to start building things, start a discussion, impose a $1 fine and be rich, or scream? So let's see if we can work this out. Who wants to start building things? That's a solid 8, 10 people, I'd say. Start a discussion. A solid bit more. Then who wants to be rich? Well, okay, it's a lot of counting if you wanna get euros for every time you hear AI, right? And then the screamers in the room. Do we have any? At least one, 2, I see. Yeah, these are all very natural reactions, and I can tell you that in the half year that I've been presenting this talk, things evolved already. There was a lot more screaming and fines in the beginning, and we are moving towards a bit more realism and a bit more perspective on how to actually include this in our work. Next question, what's your math proficiency? I'm asking this question because I want this to be an unintimidating talk. I feel challenged when I held this talk in Davos, France 2 weeks ago. It was around half of the room that agreed with me in the end that the basic math in AI is actually simple. So you guys are gonna hopefully exceed that. But first let's get to where you stand currently. For whom does it cover the basics? Well, and I suppose for everybody it does because we're going to approach high school level. I'd say at least 1/3 to half of the room. Then university grade, which is a proper quarter to the room. And we have some geniuses here, I hope. Not today. I do get geniuses raising their hand at different conferences. So anyone still inclined to say they are a genius now? All right, let's see. Now, another one that is more on typical developer traits. Who likes LAN parties, dice shots, or Rubik's Cube? See what? Yeah, there's a few hands. Just one of these. Solid 1/3 to the room. All of them. Good, 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 good. And then hardcore developers, it depends. All right, yeah, it's cheap, isn't it? So these are not here for no reason. It says a little bit about me, because I trained into IT when I was 40 years old, and I had to learn about all these topics from others. I did master the Rubik's Cube 4x4. I think I did that to impress my colleagues. It worked. And I learned only by preparing for this talk about die shots. Who knows die shots? Yeah, we're getting into that. One more question. I am in the process of developing a new talk for the next season. And I was wondering if I could get a little bit of inspiration from you guys, which one of these topics would be cool to do. So let's address them first. So I want to talk about collapsing qubits into bits. Quantum computing still holds a lot of binary. Who would say that is a great choice for a new topic? Yeah, just a few hands, 5 to 10. Now, drowning in information, how to curate quality from quantity. There's a few sets of hands, just a little bit. What's physical about the virtual? How physics of information shape our world? That's a good set more, yeah? Or dissecting trade-offs, how to calculate consequences of decisions. Well, I'm going to be an amateur physicist, I suppose. Oh yeah, sorry, I forgot to click them. A little bit about me. I'm not a mathematician, and that doesn't hinder me talking about math. So not being a physicist shouldn't hinder me talking about physics. This is me with my grandfather. He used to render fractals in the 80s, and it would take days to render them on his machine back then. One of my ancestors through this line of the family built the IJsselga Planetarium. It's the oldest still working planetarium in Europe. And these mathematical genes didn't really take me into a technical field in university. I studied communications, but later, as I retrained as a developer and started working at the Dutch Chamber of Commerce, I discovered that there actually is a lot of language in ICT, in IT, and I think we need to be aware of that. So at the Dutch Chamber of Commerce, I also started some community work. So this is one of the great stickers that we have for our Women in IT community, WeCode. And we are trying to get a lot of women on stage and feel represented at conferences. And actually, this conference is a great one. I see a lot of gender diversity. I'm very happy to see so. I'm also a community lead to the NLJUG, the Dutch Java user group, and we are organizing conferences. The next one is coming up June 4th. It's JSpring, and at the end of the presentation, I will have a code for you to get a ticket with some discount. Now, the most important thing about me is to know that I am a curious person. And that is why I want to be unveiling the simple math that powers AI. And recently, I listened to a podcast that was actually addressing how we should not mythologize AI, but it held words like it having a personality, or it having a memory, or it having a conscience. And I would think that actually attributes to the mythology. And today we are going to address how, at the core, it is basic math powering AI. So there's 3 discoveries that we're going to make. One is, underneath it all, everything is binary. It's a bit mundane, perhaps, but I want us to start at the same foot. Then AI's core is powered by simple math. Now, of course, simple is relative. So there could be cultural differences over countries, whether math is considered simple regarding the level of high school math. But we'll see how it ends up today. And then, of course, the realization that AI's answers are computed probabilities. And the reason that we call this artificial intelligence is because it has been dubbed artificial intelligence. I think intelligence holds a lot more than mimicking our language-producing systems. But what happens with our LLMs is just a lot of computed probabilities. Now, we're going to earn badges along the way, so let's go. We're going to move through the landscape. Let's see where we're headed. The big city of interaction is where we're going to end up. We'll have to pass through the valley of error and loss, to the elevated train of transformation, the point of floating ponds, and we'll start off at the numerical excavation site. So let's dive in with some basics. Numerical systems will address just a bit of it. This is a badge easily earned, I would say. We'll discuss the language of math, evolution of numerical systems, and a bit of the binary system. Now, the first thing to understand is how simple math will hold some symbolics. Of course, we all know this symbol to add stuff, this one to multiply numbers, this one to divide. Next is to raise to a power. So far, nothing new, right? And then there are some symbols that we use for irrational numbers that cannot be represented otherwise. This is not too complicated, and I want you to remember that wherever in this presentation a little bit of layers are added, still it boils down to this level of math. Then there is the matter of number structures. So it's easy enough. There's a number. In math, you could call this a scalar, and it's just a value. Then next is an array of numbers. In software, you write an array left to right, right? But this one, the vector is written top to down. This vector has two numbers, a dimension of 2, one would say. And the vector is written with any letter representing the vector with an arrow above. So this is, again, symbolics. Then we have arrays of numbers. And this in math is called a matrix. And the matrix quickly disappears. Let's see if I can get it there again. Ooh, you have to be fast, right? So it's an array of numbers. So it's just a table structure, so to say, with rows and columns. Still, these are numbers. So please be aware that whenever you organize a lot of numbers together, still, these are simply numbers. Then the evolution of numerical system. So it evolved into everything being binary nowadays, but that wasn't always the case. And let's see how this one plays out. It should actually move into the next one slowly. So in the 50s were the first binary computers with the UNIVAC to begin. A few centuries before, binary arithmetic was written, and even in 1200, Liber Abaci was produced by Fibonacci. And before that, algebra was written by Al-Khwarizmi. And in the 600, what is that? The 7th century, the positional zero took root into numerical systems. And even way before that, the base 60, So the base 60 system was developed by the Babylonians. Now, if we move on to the binary system, here we go. We have 2 digits, not the 10 digits that we use in our decimal system. We have just 2 digits. And we have the positional zero to hold a place for the several levels of numbers. So the first position is raised to the power of 0, resulting in 1 in any base. The next is the base raised to the power of 1, always resulting in the base itself, and so on and so forth, where we result in binary 1011, resulting in the number 11 in our decimal value system. Now, let's see. This was not too much new, right? First batch earned. You're still with me, or am I already losing anyone in complexity of math? No, I wouldn't say so, right? So next, we move on to the pond of floating points. And let's see what we find there. Because if we want to talk fractions, how are we going to store that in binary numbers in our computers? So when we write down binary fractions, it is very similar to the binary numerical system, only we raise it to a negative power to get halves, quarters, and eighths. So in this case, 0.011 will result in 0.375 in the decimal system. Now, as you can tell, with the binary system, you will need a lot more symbols to produce a value that in decimal notation would use less digits. So that's where we want to address how floating points are stored in our computers. Is anyone here born in 1985? Yeah, every conference room where I go, there is someone born in 1985. Well, congratulations, you are as old as a single precision floating point representation. You didn't know that, I suppose, huh? Okay, well. The single point floating presentation is the definition of a 32-bit floating point in computing. So the bits hold different responsibilities. The blue bit is the sign bit, the green bit is the exponent bit, and the pink bit is the fraction bit. Now, this is the binary number that we're going to dissect and see what it represents in decimal. Anyone already knows what this number represents? in hexadecimal, perhaps anyone recognizes it? Yeah? Seriously? What is it? I thought you were nodding. No? Okay, okay. All right, let's go. So in binary floating point notations, we are raising -1 to the sign bit to see whether we have a positive or negative number. Next, we use the exponent bit to see to what power we need to raise the fraction bit to. So using this binary number, it would mean that it resolves into a positive integer, a positive number raised to this power with these fraction bits. In this case, the fraction bit, you always get a 1 for free in the fraction bit, and then you add the half in this case, the 16th, and the 128th fraction to it. In this case, it results in 1 times 2 times 1.57. Anyone gets a feeling where we're headed? Pi, exactly. So this is the binary representation of the decimal number for pi. Now, how many digits to pi are known? Does anyone know? Nowadays. So these days, there are 100 trillion digits known to pi. Now, as one digit takes up 4 bits, 1 byte can hold 8 bits, can hold 2 digits. So we need an actual 50 terabytes to store all the digits known to pi. Now, I don't know about you, but I would rather store my fridge with pi. Now, let's see. Come again? Thank you. Yeah, I don't put sound in my presentations to ease the technicians' work. Yeah. So that is what we deal with. So digital computing with binary numbers requires a lot of storage, right? So, and the numbers that are used in AI are often numbers between -1 and +1. We are dealing with relatively small numbers in probability distribution, so they're all fractions. We'll address this later. Next, let's see. We're gonna move into the elevated terrain of transformation. So in generative AI, which I'm talking about, and LLMs, we deal with neural networks, vectors, matrices, activation functions, which are probably the heaviest math in this slide, maybe a little bit about probabilities. So this part of the talk is going to hold the most mathematical slides. But we'll start off with the simple representation of generative AI's aim. So given a certain input, what should come next? Hello, world, or hello, audience. Now, this is done on repeat, on steroids, all the time for all the input and the output. I expect this to be a familiar representation of a neural network. Is that true for everyone? Are these our hands not raised for shyness, or who knows this representation of neural images? Yeah, okay. So for neural networks, the input token is fed into the system up front. It will have an embedding dimension, and for the purpose of this talk, we limit the dimension to 2. In the case of real live models, these dimensions can add up into the thousands. Next, it passes through hidden layers towards the output, where you have the vocabulary size deciding on the size of the output layer. So at the end, in this case, we have a vocabulary size of 2. So it's either one of these tokens that gets produced as output. Now, the magic happens in between, in the hidden layers. And I shouldn't say magic, right? Because I actually want to demystify what happens here. So the addition and multiplication of numbers happens inside the hidden layers. I think actually not the math itself is special about AI, but the fact that simple math actually produces wonderful, well, not always wonderful, but okay, so let's produces text that resembles what we do as humans. So if we go into what passes through these layers. First, what happens is the token that gets fed into the system is looked up so that we get a vector representation of it. The vector representation holds the embedding dimension. In this case, only 2 features exist for the input token. These 2 features are represented in a vector, and these are fed into the first hidden layer. There it is transformed by multiplication and addition and a little bit of activation, and that results in a vector of scalars, numbers, 1 for each node in this layer. So in this case, a vector of 3 scalars. In real-life models, these are much bigger, of course, but still it is a vector with holding a certain amount of numbers. Next, in the final layer, the results from the hidden layers need to be mapped to the vocabulary size in order to make a prediction on what token should be outputted. And there, again, it's more language than it is numbers, right? So the numbers that get outputted are called raw logits, which is another word for a number. And these are used for token selection. All right, so let's zoom into the hidden layers. Let's see what transformation happens in these nodes. So one layer exists of several nodes, but if we look at one node in particular, there is a weight vector that will determine how the input is weighed. There is a bias that will actually, and these are all numbers, right? So the weight vector holds numbers. The bias is just one number that will always fire the node in a certain bias, so that has an effect on the output. It takes the input vector and it produces a scalar, just one. And it uses an activation function to break linearity. So what happens here is that we see the input vector getting multiplied by the weight vector. The bias is added, so yeah, this is multiplication and addition, not much more. The activation function is used to break linearity and to resemble our language producing system that we hold as humans, and it outputs a scalar. Now, yeah, who knows multiplication? Who knows addition? That's fine, we all know this. Who knows what an activation function does? Yeah, there's a few. Okay, so without diving into all the details, basically what an activation function does is produce something that is not always exactly mapped to the input. So there is a transformation happening that will render a linearity breaking activation on the numbers that were produced. The easiest one is the ReLU, and it's really easy, as you can tell. What it does is, for any negative number, make it 0. For any positive number, output it. Would you call this complicated math or not? It's easy, right? There are a few other activation functions, and we should consider that depending on the activation functions used and several other tweakings to the models will produce better outcomes or worse outcomes. But something like ReLU is used for activation functions and for breaking linearity. So don't be fooled. This, again, is simple math. Now next, let's see. We're heading into the final output layer. So here we are not going to focus on one node in particular, but to the layer as a whole. So where one node would hold one bias, for example, the layer will hold a vector of biases, okay? So that's what you see here. We have the bias vector, one for each node. We have the input from the hidden layer, which is the vector coming from the last hidden layer. In this case, it's 3 nodes, so it will hold 3 values that were outputted by each node in the final hidden layer. The weight matrix holds, for each node in the output layer, which is 2, 3 weights to multiply the input vector with. Now, my language might be confusing since we're still talking about numbers, but we just use a lot of words to talk about numbers. But remember that there is a representation of numbers in a structure that are still only being added and multiplied. The outcome to the final output layer is a vector of logits, so an array of numbers, we would say as a developer. And in this layer, we don't use an activation function because we want to output it to a linear vocabulary and just see what comes out of it. Okay, so this is the math-heavy slide. Who is ready? Ready to dive in? I structured this in a way that should help realize that we are dealing with multiplication and addition. So if I ask you to multiply numbers or I ask you to add numbers, you would be very able to do so. And in this case, you'd only need to know in what structure to do. So in this case, we have the weight factor. So for every node in the final layer, we have a set of weights that has the same size as the input vector from the last hidden layer, which is 3 in this case. We're gonna multiply this matrix with the input vector. So we're gonna put the weight matrix in this system. We're gonna multiply it on every row in the matrix with the input layer vector. Now, as you can tell, this adds up to a very simple sum with addition and multiplication, and it adds up to minus 1.7 and 2.3. Are you on board with me that this is still simple math? Thank you. Next, we add the bias vector. So this is even simpler math. It's just 2 values added to 2 other values, and this results in the thing called a raw logits vector, which is just 2 numbers representing the output to the final layer of the vocabulary. What happens next? We need to move from logits to probabilities. So for the vocabulary size, we want to kind of know, it's like a percentage, right? Which is the most likely output and which is the least likely output. And a percentage would be represented as 0 to 100, but you can map that to 0 to 1, right? So that doesn't really matter. If you fraction the 1, you will have 100 possibilities. The way this is being done is by using a function called the softmax, which can sound like a recipe that only certain people know the details of. But in this case, it's not too complicated. It's an irrational number risen to the power of the outputs we got, of the raw logits. So in this case, E, Euler's number, is raised to the power of minus 1.2 for the first value and to the power of 2.1 for the second value. And then we distribute these evenly across the domain of the output, and we get the probability distribution, which in this case is a very rare 0.04 for the first value and a big output for audience. So hello audience, this is what happens with every token you feed into an LLM. It gets driven through the system, it gets computed on by multiplication and addition, resulting in a probability distribution. Now let's see, this is done on steroid, on repeats. And that means that the transformation that happens inside a large language model is now something you can explain with multiplication and addition. Badge earned. Next, we are moving into the valley of error and loss. All right. So the fact that large language models are able to produce such human-resembling output is because they are trained properly. And they are trained properly not because they're not necessarily so smart, but they are conditioned properly. So what happens when we are training and optimizing the model is we are discussing error and loss and gradient descent. So if we have our model outputting a value, and we say, no, no, you got it wrong, it should be the other value. This gets pushed back into the neural system, and every node and every layer gets recomputed in order to do a better job next time. So the first time this model is trained, it will have random weights and biases and just tries to produce something that you're going to like. Then you're going to say whether it did a good job or not, and it's just going to randomly try a new set of weights and biases and see if you'll be happy next time. And this is done on steroid, on repeat, in order to produce a proper outcome. This is a mathematician's way of saying that something is off. This means that what we expected was not what we got. So this is the difference between an expectation and an outcome. In this case, for the numbers that are outputted, we are deciding on the difference, and we are raising it to the power of 2 to get a positive number. This is something often done in math, getting a positive number by raising it to the power of 2, and enhancing differences. So by raising it to the power, it will be a bigger difference between two numbers. Next, this is a mathematician's way of adding up all errors for all the values that were outputted. And then we divide it by the number of values that were outputted, which leads us to having a mean squared error. So this is just a way of describing how off the system was. And this gets fed back into the system. Now, as I said, the first run is just with a random set of weights and biases, and it's just going to see where it takes us. Next, we are randomly changing the weight in this case. So the Greek d delta stands for a difference. So we are just randomly changing the weight to, we're minimizing weight in this case, and we're just going to see what happens to the loss we get from the system. In this case, our loss increases, so we've done worse. This gives us a little bit of information because the difference between the delta for loss and weight will tell us a gradient, right? Now, the gradient descent means we are going to move away from the peak of the gradient. So now we have a little more information inside the system, and we're going to move away from the gradient. And we're going to try to minimize our loss by adjusting weights and biases. And after iterations and iterations, called epochs in training, we are aware of the best value for certain weights in order to produce the smallest loss. Who agrees with me that this is not magic, but basic computing? Exactly. But as it's done on steroid, on repeat, using a lot of computational force, you will eventually get a very well-conditioned system that is able to produce outcome that you like. So this is where we earn our badge for the valley of error and loss. And we're moving into the final phase in the big city of interaction. Let's see where that takes us. Would you say we're ready for interaction with our model? Yeah? Well, we're going to discuss parameters, model size, quantization, flops, one of my favorite words these days, and processors. So in our model, we had an example model with 2 layers, 3 nodes per hidden layer, an embedding dimension of 2, a vocabulary size of 2, which results in a total set of 29 parameters. I had to check several times again and again. The computation of the number of parameters needs to be taken into equation with what moves where. So if you want to try it again or correct me, please do later. Now, if we compare this with GPT-3, which is the final model of which these details were publicized, we get a very different number. It has 96 layers, around 32,000 nodes per layer, and it results in a total number of parameters of around 175 billion. Knowing how much memory it takes to store floating points, this requires a 700 gigabyte memory just to hold the parameters that are needed for this model. That's pretty big, right? So that means we're not ready for interaction, really. This is not a sizable model that can be operated. But then again, if we minimize parameters towards our 2-parameter example, we're going to lose accuracy, right? So there is this method of quantization that helps models, helps reduce volume of models and still produce a proper outcome. It enhances performance, reduces model size, but doesn't lose accuracy. And the Qs, Q8, Q4, Q2, are the way this quantization level is represented. Has anyone seen this in the models that you can download from Hugging Face, for example, that you get the Qs in the models? Yeah. So these are relative to the compression size for the parameters that are being used. So quantization, I would say, is a kind of a scaled squeezing. So instead of a 32-bit floating point, we're going to squeeze it into an 8-bit integer. This is Q8. It holds 8 bits. So this gives us a 25% compression, which is quite proper. And again, this is not complicated math needed to do so. You just scale the maximum value of your integer 8, which is 127, to the maximum value that you need to have represented, in this case, 7.8. So you're just going to squeeze it into the 8-bit scale. And yes, you lose a little bit of accuracy, but it results in much better performance. And this is important because we should be aware of the numbers of operations performed per answered request. So floating point operations for any model is approximately twice the number of parameters in the model, because they are multiplied once and added. So 2 operations on every parameter. Which means for the model of GPT-3, and of course the new models are much heavier than GPT-3 was, right? So we had 175 billion parameters, and let's say our input would be around 50 tokens, and our output would be around 100 tokens. It's not very realistic. We often get bigger outputs, and we often produce bigger inputs, but let's just, for computational sake, take these numbers. That results in 52 trillion flops. And that is done on repeat on steroids. So every floating point is operated on for every request you do, 52 trillion times. So it's massive. That explains why we need graphic processor units to do so. This is a die shot. It's something I learned making this talk. Who has seen a die shot? Oh, we already discussed. So would anyone recognize this as a die shot? And this is for me as a non-native English speaker, I always have to be aware that die can mean several things. The end of life, choosing what color your hair should be, and also the die that is used in games. So rolling a dice is actually the meaning of the die shot here. So all the die elements in this GPU, it's an NVIDIA GP100V4B. Sorry, I tried to memorize that. This one holds 7,200 million transistors that are switched on and off and help with all the computation. And would it be a coincidence or not that this is 314 square millimeters? What do you think? It's close to pi, right? Why GPUs? Well, as we saw, vector vector operations are very often done in these large language models. And GPUs, as graphical processor units, have been optimized to deal with vectors. Because in graphical representations, you have the X, Y, and Z axis to compute on. So you always already have a vector to compute on. So in memory, GPU can hold a vector and parallelize computing on it. For CPUs, which are general processing units, they can only hold one value for parallelized computing. And then next are TPUs, so a tensor processing unit, and a tensor is actually an array of an array of an array of numbers, so just another structure of numbers. And that can actually hold a matrix for multiplication. I didn't say that correctly, right? So it can actually take vector between computations and compute on it in matrix style. This results in considerations on the carbon footprint. This slide was not in half a year ago, but I got a lot of questions whether I was making a point of carbon usage by AI. And I don't think I need to make that plea a lot anymore because many people are aware of it. But I did do some comparison on the research that is out there. Now, it fascinates me. This research on nature.com has been cited around 1,100 times. And it addresses that in the green box, we have the excellent performing, low energy, low pollution AI models. And on the far right side, we have the very, very polluting humans. Now, there's something off about this research because it is disregarding quality of output. So someone said today it's a code vomiting machine. If we were code vomiting humans, we would be out of a job. But for AI, we consider that proper. The other issue is that it eliminates human emission when using AI. Now, in order to eliminate human emission, we need to eliminate humans. It's questionable whether that is the purpose, right? So this article that I saw first was cited by the next article. The next article didn't get cited itself as much, only 8 times. And I want to ask you later to write it down and see if you can share this research online. It was done by someone that incorporates quality of output by actually using the American Olympiad for programming, which is very well documented, and you can actually really compare the quality of output of the humans that participated in it and the AIs that you let perform on it. And it computed for the continuing human emission, whether we use AI or not, which is a relief to me personally. This research was done by a 16-year-old student in California, Nolan Wu. I contacted him. I was fascinated. He hopes to enter the field of computer science. And he is kind of worried about what his job is going to look like, as we are all already today, from time to time. What he researched was that if you take quality into account, if you assume humans will continue emitting CO2, then what you see here is the green fields are the human result, and there's only a few models that are actually performing much better when you take into account carbon emission. He pleads for being selective. He pleads for select the right model for the right task, or no model if a human would be better at the task. Please help sharing his research. I'll let you take photos of this slide. So there are strict rules about when this number is going to go up, and it needs to be published in certain online domains to get more traction. So let's see where we can take Nolan. And that earned us our badge for the big city of interaction. So that means we've zoomed on to the very different sides from basics to what happens inside the node, to how it's outputted and how it's used. And there's still quite a lot of terrain uncovered. So there is so much around AI that addresses other parts that play a role. But I hope you can agree with me that underneath, everything is binary. AI's core is powered by simple math. And AI's answers are computed probabilities. So who here agrees that it is simple math at the core of AI? Yes, you're performing better than France. Thank you. That's a proper 2/3 of the room. So thank you so much. You've earned your badges, and I have many research sources, yes, also AI, to thank for producing this talk. I'm hoping for 20 ratings, which is kind of representing for the room, so I can be aware of how to do this talk next time. And as promised, the J Spring discount code. It's June for in Utrecht in the Netherlands. It's only a 3-hour train route from here, so that's quite doable. And you'll get a 20% off if you're using this discount code. Please feel free to connect, and thank you for your attention.